LT Spice is a freely available simulation tool from analog devices which you can download. It is fairly easy to download. Look for LT Spice download and Google, and you will be able to download and install. And they also provide a lot of examples. Okay. So, this will start a new schematic. Okay. So, file new schematic, and let us draw a very simple circuit maybe. You can see that you can add resistors, capacitors, inductors, diodes, and a lot of different kinds of components. You can connect these with nets, and then this is how you wire them together, and you can label these nets. You can add text. You can add SPICE directive. SPICE is a simulation program. So, LT Spice is basically built on top of a simulation program called SPICE, but they provide their own nice looking GUI like this, right. So, let us start with a very simple one. Maybe we will take a component. So, you will see lot of different components. Okay. There are ADCs, op amps, DACs, and so on. So, let us take a simple thing like maybe a op amp. If you there are many op amps. So, these are depending on the company. So, they seem to have created models of many op amps from different companies. I think these are generic ones, universal op amp. Okay. So, these are generic. You can search for any specific one. Let us pick one of these. This is a generic one, op amp. So, if you say op amp, you can see that it only gives you the minus and the plus input terminals, okay, and the output. The biasing etc. are not shown, okay, because to keep things simple. Whereas, if you take a real op amp, okay, maybe LTC something, it shows the entire IC. If you take LTC 1058, it shows you minus plus, and it also shows you the positive and the negative. Okay. So, let us just take and then it also shows you open example circuit. Okay. So, they already have an example circuit. So, this is a 6 decade log amplifier, logarithmic amplifier. Okay. Let us not do this one, let us do a simple one. File, new schematic, select an op amp, let us say LT 1050A. So, you can place it anywhere you want. Then you can place voltage. Okay. You can use the right click of the mouse to cancel it. See, if you want to duplicate anything, okay, you can select this and say I want to duplicate here. If you want to cancel that, right click. This will move things. See, if I want to move this guy somewhere else, I can move it. Okay. This symbol means copy it, this means move it, and then you can also delete. I want to add a voltage, okay, and when you bring in any component, I think control R will rotate it, is what I remember. Control R, okay. If you apply control R, it will keep rotating it by 90 degrees. So, in this case we would like to have positive to positive, okay. And maybe we will have one more voltage which is negative. So, you can click on this to set its value. If I right click on a component, I can say, look, I want this to be 15 volts. So, that may be the rating of this particular, typically op amps have 15 plus 15 and minus 15. You can also specify a series resistance if you want, and this also, let us say it is 15. I think there is a way to adjust this font also. To add a ground, you have to use this. We need a ground here also. So, let me make let me rotate that ground. Okay. So, ground doesn't seem to rotate. So, we will have to use a net. So, use a net to connect it. Okay. This means zoom to fit, okay, and this means unzoom. Okay, so we have biased this op amp. Now we will have to add. Let us say we want to make a inverting amplifier or something like that. Keep it simple. So, let us say we add a resistance of 300K or something like that. So, control R will rotate. Then let us add net to connect these guys over here, right? Yeah. Okay. And then you have to add a voltage source, which is the input. I believe we have finished laying it out. Only thing is we have to adjust the resistance value, etc. So, let me make this resistance 30K. Tolerance can be 5%. This one is R2. We can make the resistance maybe 5K. So, the gain is about 6, I think. Then maybe also 5%. Okay, we have a 5K, we have a 30K. Let us change the voltage, the DC value. I think you can also say advanced here, and select sinusoidal voltage. And you can say the DC voltage, the DC offset is 0. That means there is no DC as part of this voltage. The amplitude can be maybe 1 volt. Frequency can be 1K. And so you can say it is a amplitude is 1 and no DC offset, and 1K is the frequency. We can label the net let us say we call it out, and you bring it wherever you want to label and you say it is out. Similarly, you can label the input as in. Okay. So there are 3 types of analysis. See, this we have drawn the circuit, but what do we do with this circuit? We want to analyze the circuit. Let me remove this slide. You can adjust the analysis you can say I want to do transient analysis. Transient analysis means you want to look at the output as a function of time or the input as a function of time. Okay. When the inputs change, how do the outputs change? So in this case, maybe let us go ahead and do transient analysis. So this is sine omega t. Okay, its amplitude is 1. So sine omega t, where omega is 2 pi f. So in this example, f is 1000. So that is what it is, sine omega t, where omega is 2 times pi times 1000. We can say since it is 1 kilohertz, each period is 1 millisecond. So maybe we will simulate it for about 2 milliseconds or maybe 5 milliseconds. Okay. 5 milliseconds. The time step can be maybe 10 or 100 microseconds. So that means we will sample it every 100 microseconds. So if you want to make it more accurate, you can make it 10 microseconds. So you can see that it brought up this and we can put it here. So dot tran, start from 0, stop at 5 milliseconds, and use 100 microseconds as the precision. That means take snapshots every 100 microseconds. Okay. See, now we can go ahead and simulate this circuit. So when it is done, it will show you a window. Okay, you can adjust the window. You can say I want the window side by side. You can also say I can one below the other and things like that. So how to see a waveform? You can see the pencil mark. So click that. So it is showing you the input waveform. So this is V in. You can also see the output waveform. Okay. So V in is green and V out is blue. Okay. So you can see V out is blue and V in is, So, there is a factor of 6, isn't it? I mean, we had adjusted this to be 30K. So, 30K divided by 5K is 6, and here it clearly brings out the phase difference, right. It is a 180-degree phase shift. When the input reaches its positive peak, the output reaches its negative peak. Okay. Now, the thing is, the output looks a little distorted. Okay, it does not look like a perfect sine waveform. The one reason could be that the analysis that we have done, we have done 100 microsecond snapshots, right. So, we can try and change that and say let us change it to 10 microseconds. So, it will take a little longer to simulate, but it will be a little bit more accurate. So, it has changed to 10 microseconds. So, if you simulate it now, I do not know whether it seems a little bit more, but there seems to be still some distortion. Okay, that could be because of, let us see what could be the reason. Okay. Now, we can go ahead and say view, we can select one of the waveforms. Let us say we use V in, okay. And then I think once you select it, you will be able to see. So, once you select it, you can see its FFT. So, FFT of both input and output, and this may be too accurate. So, let us reduce it, maybe 8,000 samples is good enough, right. And say OK. So, this is our FFT of the output. So, you can see that at 1 kilohertz there is a big peak. Okay. So, the input is a 1 kilohertz waveform. So, the output also has a very strong 1 kilohertz waveform, but unfortunately there are other components here. Okay. So, you can see that there is another peak. At the bottom you will see the frequency. If you can see that it is a 48 kilohertz or 50 kilohertz waveform. Okay. So, there is a little bit of a harmonic. There may be a small peak here at 10 kilohertz, and these are all harmonics. So, the output here does not look too bad, it looks like a sinusoid, but that is to the naked eye. But if you really go and analyze using fast Fourier transform, you will see that there is some harmonics, there are some harmonics. See, the output is 6 volts. So, its gain will be 20 log 6, I believe, okay, that many decibels. Okay. So, there is some harmonic and it may be coming because of the op amp itself. We can see if the input is good. Okay, let us go ahead and look at the input. So, you can select the input and then I think the FFT was already done, but let us do it again. View the FFT, do only the V in. Okay, let us do it for both. Can use shift to select more than one. Perform the FFT. Let us only look at V in. See, even the input is not that great. You can see that there are some, the input itself has some harmonics. it is a strong component at 1 kilohertz, and the gain is showing up as 0 dB. See, we chose 1 volt, remember, the input was selected to be 1 volt. So, that is the reason it is showing 0 dB, 20 log 1. Okay. These are not very strong. See, these are very small. It is only about minus 60 dB or something like that, in comparison to the main component, or what is called as the principal component, or these are small, but they nevertheless they are there. So, these get amplified and they will cause a little bit of distortion in the output. So, this is our transient analysis, and we know how to do the FFT and things like that. So, my thing is I can't show you an ATE, unfortunately. There is no automatic test equipment that I can bring and show you. So, I am trying to do what is best alternate. So, this is at this point of time just a model, isn't it? It is not a real IC. Okay. It is just a simple model in a simulation program.